One of the most well-known circle theorems is the inscribed angle theorem. There's a relationship between the inscribed angle and the intercepted arc, in this case arc CD. Earlier I measured the degrees of the central angle here, CBD, and that was 44 degrees. We know that the central angle equals the arc measure, so the arc CD has a measure of 44 degrees. But how many degrees is angle A, CAD? Well, I measured that earlier, and that's 22 degrees. So just based on this one example, we can see that the inscribed angle is half the measure of the intercepted arc. And that's true for every single inscribed angle. It is half the measure of the intercepted arc. Right now you're taking that based on one example, but let's come up with a level 4 argument to show that it's always going to work. Okay, so we are given circle B. We want to prove that the measure of angle CAD is half the measure of the intercepted arc. I'm going to erase the angles here because we want to make an argument that's true for all cases, not just for one case. Okay, so circle B, that is given. Next step, BA is congruent to BD. That's because, so BA is congruent to BD. Those are radii, and we know that all radii of circles are congruent. That leads us to, well, look at the picture. We have an isosceles triangle. So triangle ABD is isosceles, and that's by the definition of isosceles triangle. Which leads us to, gave you a hint here, the isosceles triangle theorem. Base angles of an isosceles triangle are equal. So therefore, the measure of angle BAD is equal to the measure of angle BDA. Okay, meanwhile, we have another relationship here. The measure of angle CAD, angle here, I'm going to shade that in so we can see it better, plus something makes the measure of CBD. This was always a kind of a tricky step for students, but if you think about it, if you really look at it, and I cover other parts up, I have a triangle here where one side's extended. That angle is outside the triangle. That's an exterior angle. So this angle, angle A, plus the angle right here by D, add those up, that will equal the outside angle. So the measure of angle CAD plus the measure of angle BDA will equal that exterior angle, and we're going to be using the exterior angle theorem. Okay, well, both of these angles are congruent because I have an isosceles triangle, and so putting together the exterior angle theorem step with the fact I have an isosceles triangle means I can just substitute one angle for the other, and in this case here I substituted angle CAD in replace of angle BDA. Okay, next step. Well, this leads to something, but I need something else before. So I have a central angle equal to the arc measure. So we must be referring to the central angle CBD. So the measure of angle CBD equals the measure of the arc CD. Putting these steps together, looking here, I can replace the angle here with the arc. So 2 times the measure of angle CAD equals the measure of the arc CD by using substitution. Well, we're almost there. To go from the second to last step to the last step, it looks like I multiplied both sides by 1/2. So I use the multiplication property of equality. Therefore, in this argument, we have shown that if I have an arc, the intercepted arc of an inscribed angle, the inscribed angle is half the measure of the arc. I first did it by looking at it as an experiment, one example, but I also was able to prove it to show that it works in all cases here. There are actually two more arguments you have to make for the inscribed angle theorem, but this is like the easiest case. We're not going to go into the other ones. They can get pretty in-depth. Okay, let's apply the inscribed angle theorem. So in both of these diagrams, I want you guys to solve for x. Okay, so you got to look at the picture. 42 is an inscribed angle, and we want to solve for x, which is the intercepted arc. So we're going to justify. I'm going to be using the inscribed angle theorem, and I know that the inscribed angle, so measure, let's see, angle ANT, so the measure of angle ANT is equal to half the measure of the intercepted arc. Okay, so I've justified, I've written my first step using the names of the parts I want to use. So let's substitute. So 42 degrees is the angle, equals 1/2 the measure of the intercepted arc. Multiply both sides by 2, therefore the measure of that arc is equal to 84 degrees. Last example here. X is representing the inscribed angle. I notice that 135 degrees is a central angle. So by looking for these details, it's giving me a kind of a clue here what to do. So I have an inscribed angle and a central angle. Well, I know that theorem we just proved. I do know the central angle equals the arc measure. Oh, well, if I can figure out the measure of arc AF, then I can figure out the measure of the inscribed angle. So we're going to have two justifications this time. So since I know the central angle, I'll use that to find the arc, and I'll use the arc to help me find the inscribed angle. Okay, so central angle equals the arc measure. So the measure of arc AF equals the measure of angle ACF. So the measure of arc AF equals 135 degrees. Then I'm going to apply the inscribed angle theorem. The measure of angle AUF is equal to half the measure of the intercepted arc AF. So the measure of angle AUF is equal to 1/2 of 135 degrees. Oh, I should probably plug in x here, shouldn't I? So x equals, take my calculator, 135 divided by 2. We get 67.5 degrees. And I didn't quite finish the answer over here because we were solving for x. So x equals 84 degrees. Okay, so what's going to get you full credit? You justify. The next thing you write is using the actual names. I'm requiring that you do this so that you get practiced with understanding this notation here. Okay, you show work, get an answer. Once again, justification, show me the first setup using all the names, substitute, and then give me the answer.